I want to talk about Hansen solubility parameters and how they link with IGC, and I want to show a new way in which we can all explore the possibilities of IGC. This is me. Again, sorry that I can't be with you in person. One of the things we have to do as a community is formulate for compatibility. We need compatibility to dissolve a polymer in a solvent, combine two polymers, disperse a pharmaceutical in a polymer for controlled release, disperse nanoparticles in solvents and polymers, for example for paints and inks. So if we want to formulate for compatibility, how do we calculate compatibility? Well, too often we use crude ideas like hydrophilic, hydrophobic, polar and non-polar. You just can't calculate with those. You can do quantum mechanical calculations, but that's too time consuming for most of us. So we know that like is compatible with like, so how do we calculate like? The answer for many of us, and it's worked for 45 years, is to use Hansen solubility parameters. Every solvent, polymer, pharmaceutical, nanoparticle can be described with these three parameters. The first one is dd, which describes the dispersion, the van der Waals forces between molecules. Every molecule interacts with every other molecule via dispersion. It's a fairly boring force, but it's very powerful. It's what keeps most things together. It depends on the number of electrons sloshing around the molecule, i.e. on its polarizability, and dd is not some artifact dreamt by Charles Hansen. It has a very strong correlation, for example, to refractive index, which you can measure. dp is polar, i.e. our normal idea of polarity, and it corresponds very strongly to dipole moments. And then dH is the hydrogen bonding with which we're familiar. So with these three parameters, there's nothing complicated, obscure or surprising about them, and as we'll see, they're pretty intuitive, and we'll see it live. So I have here HSPIP, Hansen Solubility Parameters in Practice. It's software I've written. It's very good software, but I'm not here to sell it. I'm using it to describe HSPs. We have a bunch of solvents, for reasons I'll describe in a moment, and each of them has three parameters, dd, dp, dh. And if I click on the top of the dd column, it sorts them from low to high. As I said, dispersion is everywhere, so even dull molecules like ether and methanol hexane have a fairly substantial amount of dd. They're held together by it, but the numbers are quite small compared to something like pyridine, which with that aromatic and the lone pair on the nitrogen has a lot of electrons sloshing around, a large refractive index. Cresol is another aromatic. DMSO has that large sulfoxide group and a high dd, and so forth. Furan is 17, cyclohexane is 16.8. Then there's dp, the polar. Not surprisingly, hexane, cyclohexane and benzene have none of it. And at the other extreme we've got acetonitrile, which has got 18. And that's methyl carbon nitrogen in a straight line, a very high dipole moment and a very high dp value. Something like methanol is intermediate, acetone lower, and so forth. Then we have dH, the hydrogen bonding. Hexane has none of it. At the other extreme we have water, which is full of hydrogen bonding. Methanol, not surprisingly, and then ethanol's hydrogen bonding is rather less than methanol, simply because it's diluted by the extra CH2 group, which distinguishes ethanol from methanol. If I go back here, we find that benzene and toluene have a modest DH value, which is very surprising to people. Charles Hansen was laughed at for saying that he'd found these values experimentally, but recently it's been confirmed that aromatics are reasonable hydrogen bond acceptors, so it was wise of Charles to go with the experimental data and include them. So those are the HSP, nothing very scary about them. What do we do with them? Well, we can calculate likeness with them. We calculate the distance, the HSP distance, sometimes called RA, which is the simple distance in 3D. So if one entity, say the polymer, has D1, P1, H1, and the other, say the solvent, is D2, P2, H2, then the distance squared is the sum of the squares of the differences in dd, dp, and dh, with a famous factor of 4, which privileges the dd values. So as long as you know these values, then you just subtract each of them, square them, and that's the square of the distance. And obviously, if there's a big difference between each of them, That gives a large distance, and a large distance means incompatible, and a small distance means compatible. And you can have a large distance, for example, these might be similar, but if one has no hydrogen bonding and one has a lot of hydrogen bonding, this term will be large and therefore the distance is large. Or they might all be modestly different, but the sum of all those modest differences adds up to a significant distance. So there are many ways in which things can be incompatible, and of course relatively few ways in which they can be compatible. And the point is this distance calculation works for solvents, polymers, cosmetics, nanoparticles, skin, food packaging barriers, organophotovoltaics, paints. These are all places where I personally have used HSP to good effect. So, all we need to apply this powerful concept are the HSP of our materials. So, where do these values come from? Briefly, for solvents, it can be done via thermodynamics. If you have the enthalpy of vaporization, refractive index, dipole moment, you can calculate these values quite well. For solids, for polymers and nanoparticles, there's a standard technique, I loosely call it the 20 solvent technique. You get 20 test tubes, you put a small amount of the polymer or whatever into the bottom of the tube, and then put a different solvent in each tube, shake it, leave it for a while, and then score 1 if the material is happy in the solvent and 0 if the material is unhappy. Why am I using such unscientific terms like happy and unhappy? Well, if the polymer is a normal polymer and is soluble, then you'd score 1 for soluble and 0 for insoluble. But if the polymer is cross-linked, it will never dissolve, but it might swell. So you would score 1 for swelling a lot, so it's happy with the solvent, and 0 for unswelling, and so forth. And once you've got this list of solvents, you find the HSP value, which means that all the good solvents are inside a sphere centered on the HSP of that material, and all the bad ones are outside it. So that defines the HSP and the radius, which shows how choosy the material is. This will all make sense when I go live. As I said, I had these solvents for a reason, and that is because some academics scored them 0 and 1 for polylactic acid. And if I click this magic button, then it calculates this sphere in 3 dimensions, and all the good solvents, all the ones, are in blue and they are inside the sphere. So for example, pyridine is there, NMP is there, and DMSO is right on the outside. And all the bad ones, such as acetonitrile, are outside. They're the ones in red. And this is a unique fit because if the center, this green dot here, were to the left, a higher DD value, then some of these blue ones would be outside the sphere. If it were more to the right, then some of these red ones would be inside the sphere, which would also be wrong. So there's a unique fit, and this radius depends on your definition of solubility or happiness. And this also works for things like carbon nanotubes. So here I have a test tube with a solvent which really rather likes carbon nanotubes. The whole test tube is black. It's been sitting like that for weeks and months. I've personally seen these test tubes. They're from Dr. Simon de Trich in the University of Namur. And you don't need to be an expert in carbon nanotubes to know that this solvent and carbon nanotubes just don't like each other. The CNT are just sitting at the bottom. So that's a 1 and that's a 0. This, when you see the picture close up, is borderline, so you might score this as 2, and this is borderline, so you might score this as 5. And if we go back to the software and I load the data set for carbon nanotubes, and I define the inside as just the ones which are scored a 1, then I do the fit, and there's a small sphere for carbon nanotubes, 27.3, with a radius of 2.5, so a small sphere, just a radius of 2.5. If I allow these intermediate ones, these 2s, to go in, then, not surprisingly, I get about the same value, 27.4, but the radius is larger. So that's how we measure it for solids. That brings us to IGC. This standard technique is very bad for liquids, such as the pharma cosmetic excipients or oligomers of polymers. They're too soluble in too many solvents. So if you try your 20 test tubes, 18 of them you'll find they're soluble or miscible. But if you can do an IGC experiment, if you can put this semi-liquid onto the stationary phase, and if the interaction of the IGC probes depends on how like or unlike it is, then the unlike will elute quickly because they won't want to spend time in the stationary phase, and if they're like, they will elute slowly. Now, of course, you have to correct for vapor pressure, molar volume, and things like that, because small light molecules will elute fast for other reasons. And if we can get this IGC method to work, it will revolutionize the measurement of HSP. The talk from Sander van Loon from VLCI, he has actually helped measurements of HSP by using his standard techniques, and this is really valuable, and he's been able to push it towards liquids. But if we as a community can do it via IGC, that will help all of us. So, how can we get the right correlation between retention and HSP? So, how might IGC work for HSP? Well, to answer that, we have to step back, because we need to understand some rather complicated things. And there's an app for that. Abbott's rule now is no science without a formula. That's fair enough. But no formula without an app. And I'm trying my best to live by this rule, because I've created my Practical X series, Practical Solubility, Practical Surfactants, adhesion, where I have packed in as many formulae and bits of understanding that I can, and they're all brought alive with an app, which you'll see in a moment. They're all at stephenabbott.co.uk Abbott apps. They're all free. There's no adware, cookies, or anything nasty. They run on all devices, PC, Mac, tablet, phones. They're safe for corporate networks because they're just HTML5, JavaScript, and CSS3, so they can't do any harm to things. Now I've started to construct practical chromatography with considerable help from AdScientist and Inolytix, which I most gratefully acknowledge. So let's go live to these. And here's practical chromatography, and I'm on the IGC basics. There's very little else in here at the moment. And here's a typical page, so it's an ordinary web page. Here's some nice pictures describing GC and IGC. These are from AdScientist. And this particular page just explains one thing, which is VG, which is the specific retention volume which we will use in subsequent apps. And that's defined as J times TP minus TM times F of W. J is a compressibility factor. It's just normalizing the values to express what this particular probe molecule would do on a standard amount of stationary phase on the column, so that VG values from one experiment can be replicated on a totally different machine within another experiment. And the important thing is that the free energy of interaction of the probe molecule is RT times log VG. So VG is a thermodynamically profound value which is intrinsic to the IGC measurement. Okay, that's a background one. Now let's show this doing something for real. Measuring the dispersive energy of a stationary phase. Here's the experiment. We would inject different probe molecules, pentane, hexane, heptane, octane, for example. And these are the retention times, and then these are translated into VG values, as I said before. And then you can say that the dispersion surface energy, gamma S, depends on the dispersion surface energy of a pure CH2 group times Avogadro's number times the area of a CH2 group. And the delta G CH2 is the average change in delta G per CH2 group. That's all very hypothetical, but now we can put our values in. Let's say for pentane it had a VG of 25, and for heptane it had a VG of 190, and nonane was 900. We get this graph. There's some experimental error in it, but there's a best line straight fit, and it tells us that the gamma S, the dispersion energy of this particular material, is 34.9. And if you've done it on typical polymers or cellulosics, calcium carbonate or whatever. Now that's if I'd measured at 53 degrees. If I'd happened to measure it at 40 degrees and had these same VG values, then it would be 30.8. So this is allowing you to see the effect of temperature on measurements. So all the temperature does is change the delta G values of all of them. You can see those being calculated from the VG, and therefore change the value there. So that's just dispersive surface energy. What about surface morphology? Well, there's been a paper published by Brendley and Papire which says that let's find a bunch of standard materials, pentane, hexane, heptane, and so forth, and there's the graph that we saw before. And let's put in a probe which has some branching in it, for example 2-methylheptane. So it will not be able to fully fit onto the surface, and if there's a rough surface, it'll be less able to fit into the roughness than if it was on a smooth surface. So there's a value chi t which defines a parameter for N-methylheptane, 7.9 in this case. Here's a list of some others. And what you do is you inject the 2-methylheptane. We know that it should, if you had a perfectly smooth surface, come out at 7.9, straight on this line. But if the VG of this probe happens to be, let's say, 53.9, then it's actually coming out here. The delta G of interaction is much less. That means that it is not fully able to interact with the surface. And there's a morphological index, IM, which is 0.15, which is saying that this surface is so rough that even a small amount of branching from 2-methylheptane is enough to cause it problems. If the VG of the probe took us closer to there, then you're saying actually it's not too rough. So here's a way of beginning to explore the surface, and then if you want to look at specific interactions, polar interactions, then you start using other probes like, for example, toluene, which has a 6.3, so I'll give it a 6.3 there. And if the VG was, for example, 362, then we're saying there's an extra polar contribution of 4 kilojoules per mole. So that's what I'm trying to do with the apps, the IGC apps, to bring these rather complicated ideas alive so you can play with the values. So this at long last brings us to HSP. And what we're saying is that the link between the probe molecule and the surface is the Flory-Huggins chi parameter, which is given by all these complicated things. But basically it's allowing us to measure the interaction, the chi parameter, between the probe molecule and the test material. And if you can calculate the chi values for a bunch of probe molecules against your test material, then you should be able to fit them to some formula. Now it happens that the HSP distance is related to the chi parameter. So we calculate the chi parameter from the IGC experiment. We then say what the D parameter is, because we know the molar volume and RT, and we can then try to fit it. And here is the experimental chi values for these particular probes done by Tian and Munk. And if I guess that the DD is 16, DP is 13, and DH is 5, you'll see there's a pretty lousy correlation. But if I then play around with these, obviously one could automate this with the least squares fitting, but I'm just currently doing this manual, it's actually quite instructive. Then once I start getting some around here, then I've got an R squared of 0.87, which isn't bad. So roughly speaking, the D, P and H of this particular thing, which is polycaprolactone, is around the 1965 area, which is data we have from other areas. Had this been measured at different temperatures, then everything swaps around. So this happened to be 70-degree data, and there are corrections for the density and the molar volume and things like that. So what I'm saying is that we as a community can start measuring HSP values using this sort of technique. But there's a problem. Some very recent data from Dr. Brendley has shown that for some excipients, the attempt to fit it via this chi parameter is not just slightly wrong, it's not It's not something like that. It is catastrophically wrong, which means there is an error in our chain of logic. And hopefully in your discussions you'll be able to find that error, because once we can fix it, then and we can go from VG values to something like chi, then we can start measuring HSP values. So, next steps. I really want you to explore my practical sites in areas that interest you, solubility, surfactants, whatever. When you explore them, please feedback problems, issues, wish lists. I love fixing things, extending the apps, writing new ones. But in particular, what would you like to see within practical chromatography and IGC specifically? For example, one suggestion is that instead of using VG, I should use retention time. But that's up to you. So over to your questions, if the live technology works.